All right. The question was on the research paper. I said one full page of text. Now, a good question would be, what do I mean by one full page of text? So if you have a header at the top, and you don't have to, but if you do, that's fine. And then you have the title, and maybe skip a few spaces, get a title, and then triple space, and then start typing. Now, you don't have to do it this way, but if you do, and you start typing here on that first page, okay, to get one full page of text, you're going to go to the bottom of that page, and on the top of the second page, come down at least that far. So you're going to have two pieces of paper at least to have one full page of text. Does that make sense?
Yes.
Okay, so yeah, and I say shoot for 1 to 2 pages. If it's anything short of 1, you will lose points. Okay, if it's anything over 2, you won't necessarily lose points. I don't take off for too much work. I only take off for not enough. So if you get really carried away and you're really interested in your topic and you can't find a good place to stop and you go into 3 or even 4 pages, I don't care. You know, as long as it's a good paper, give me a good paper. But at least one full page of text. And then was that all of your question, or was there a second part?
That was it.
Okay. And then also, of course, your
It was about the source page.
yeah, your works cited page or source page or however you want to call that. And remember, you have to turn in at least a single sheet, 1 page from one of your sources. Hopefully you have 2 or more sources, but whatever you have, pick a source, pick a page, and send me that with your paper as well. All right. Any other questions? Good question, by the way. All right. If not, I see no okay, Jordan, you have something else? I saw your light come on.
So that one page from our source, do you want to copy and paste it? Take a screenshot of it?
Okay, however you can get me a page. Okay, if it's something you got off the internet and you can print a page there and attach that to it and send it, that's fine. A screenshot would be fine. Is that with a camera, or is that actually a computerized thing when you say screenshot?
It's computer thing.
Okay, yeah. So if you can attach that, that's fine. If you have a page, if you actually got to a place on a library source, you know, even though you probably can't go to a library, but if you could, or get something off the internet from the library and you can't actually print a page, well, however you can get me one, a picture, however, just a page from a source. Good deal. Good questions. Any others? All right, well, if not, let's go on and get set up for starting the class. And we are starting in 5.4 and example 10. We'll start the slideshow from this current slide. Okay. Any questions on calculus before we get started? Okay. This was a setup. And we had answered the first part. Here's the velocity in feet per second of a particle moving along a line. And the velocity is a function of time, t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. And the first question is, what is the displacement of the particle on the time interval 1 to 5? Okay. Now, we did that, and basically that's just the integral of v of t. Okay. And that gives you, because v of t is ds dt, and so basically you're doing, you're integrating that from 1 to 5 seconds, and that gives you s, the total displacement. However, that doesn't necessarily give you the total distance traveled, because in that time frame, and we looked at this and found out it started, I think, going positive and then went negative and then positive again. No, didn't go positive again, but it went back to 0. Okay, therefore the total distance traveled, so a positive displacement would be going this way, then a negative displacement here, and then back here. Hey, that's going a greater distance than just its final displacement. So that's what we were doing the second part. And let's see, this was the first part. When you just integrate the velocity from 1 to 5, that gives you to total displacement. Okay, and we did that and got that, and that came out 128 over 12, which you can reduce to be 32/3. Yes. Okay. All right. And that was feet to the right. That's your total distance. Now, that doesn't really sound like that far. You know, that's just over 10 2/3 feet. Okay, is all it moved. Okay, but this was a weird velocity it had, so that makes, I guess, good sense. On the B part, so that moves 10 2/3 feet to the right, total. To find the total distance traveled, you need to calculate the absolute value of that velocity. So everything, you don't count a negative velocity as backtracking. You say, how far did it go backward and then back forward again, or whatever. So in this case, they drew the graph. I think we did too. This was the positive displacement from 1 to 4, and then a negative displacement here. Well, to get the absolute value, you would take this little hump here, and absolute value would make it a positive amount. Okay, because the absolute value of this one is itself, okay, because that's always positive. The absolute value of this one, because it's negative, that would be the hump that would be just about like that. Okay, so we have two pieces. Now, we didn't factor this, if I'm remembering correctly. Oh yeah, we did, when we found out what the zeros were. We did that. Okay, we found out the zeros, and sure enough, they were 1, 4, and 5. Okay, we found out that it was positive between 1 and 4 and negative between 4 and 5. I think we all remember doing all that. So our integral then, the absolute value one, would be the integral of v of t from 1 to 4, because that's your positive amount, and then the opposite of that, the negative, from 4 to 5, because this gives you, from 4 to 5, this would give you a negative displacement. Well, we negate that to give you a positive displacement. Okay, and I think we had done this next step, and we integrated. Yes. Oh, you can't. I'm sorry. Oh, I wish you'd have said something sooner. Okay, I don't know where it's gone. Okay, hold on just a minute, and let me see. I'll minimize this. Now I can see Zoom. Okay, I thought we had done this before. Okay, I guess not. Here we go. And still nobody's waiting. Just 3 of you here. Got you all 3 here. I thought for sure I clicked on this, but maybe not. Okay, thank you. I'm going to have to move this taskbar out of my way. I know you can't see it, or I don't think you can. So it's kind of out of my way now. I'm going to also need to slide Andy over. He's just always in the way. There, he's off the side. You can't see that. Your 3 names and my picture are there on top. Okay, so this is where we left off. So let's go back to the slideshow from current slide. Come on, from current slide. There we go. All right, sorry about this. Let me back up then. Okay, here's the problem. First the displacement, and then the total distance. Displacement is just simply the integral of the velocity, because velocity is ds dt, where s is your displacement. That gives it to you. Integrate the ds dt, you get s. Okay, so that's what you do. You leave it in this form. But, and there is where you do it, and I think we had already done that and got the 32/3 of a foot to the right. 10 2/3 feet to the right, which is not a bad displacement, I guess, in 4 seconds. Okay, so Second part though, the total distance traveled, you do the absolute value of v of t. So in that case, and we did this last time, we found out that it had a 0 at 1, a 0 at 5, and we then discovered it had a 0 at 4. We checked and made sure it was positive in this range. It was. And we just verified it was negative here. It was. So therefore, you do the integral of this part, and that gives you the displacement between 1 and 4 seconds, the distance traveled in 1 and 4 seconds. To get the distance traveled here, rather than subtracting this from that, because you see this would have given you a displacement in the right direction, then this would turn around and move it in the left direction. You would have ended off back here. Now this is a time scale, so, and that would be your 32 thirds of a foot, 10 and 2/3 foot, somewhere back here. Well, we want total distance traveled. So you went positive distance here, you went a negative distance there, but it's still a distance, okay? So what we do is take the integral of the absolute value of this, which this, of course, that will be its absolute value. Here you do the positive of that. You just flip this over the x-axis and integrate that part. So that's the negative of what you've got here. Because here it's below the x-axis, the negative of this will be above the x-axis. And that's why this second part of the integral, this part has the minus sign in front of it. Because you're still integrating that velocity, but you're doing the negative of it because that was a negative velocity, total distance travel, and that would only be from 4 to 5. 1 to 4 for that positive hump, minus the 4 to 5 for the negative hump. And that, I think, is where we left off before. This gave us the integral here, same integral we had before, same antiderivative, but different bounds. However, this one flips everything. This integral will be the same, but then it will negate it, okay? And that's about where we left off last time. So I'm going to get my stylus, if I can uncover it here, move my phone down here out of the way. Said I had a missed call 18 minutes ago. I don't know who that could have been. I was here, but I must have been in the restroom or somewhere. I probably was. I had gone downstairs right before class to pick up something. So, whatever that is, I don't mind missing the call. Okay, let's do this integral. We did it last time. I'm going to give us a little more room here and start over here. What's the integral antiderivative of t third? Anybody? T to the 4th over 4. Simple power rule. Minus, and this will be 10 t cubed over 3 plus 29 t squared over 2 minus 20t. That's evaluated from 1 to 4. Okay. Minus, okay, I'm going to put this in parentheses here, same as we had before. T 4th over 4 minus 10 t cubed over 3 plus 29 t squared over 2 minus 20 t. This one is evaluated from 4 to 5. Okay. Now I guess maybe I should put all this in parentheses too, or at least that part of it. Alright. Now, the rest is grunt work. Okay? And I'm real tempted to just pull out my calculator and do it, unless you'd like to see it, the numbers written down, would you? Well, if t is 4 to the 4th power, 4 to the 1st power is 4, second power is 16, third power is 64, and the 4th power is 256, I believe. So this will be 256 over 4, which I think is just 64. Now you'll have to check my math here. I'm doing it in my head. Minus, okay, and this was 4 to the third, which is 64. That would be 640 over 3 plus t squared, 4 squared is 16, 2 goes to 16, 8. So this is 29 times 8. I'm not going to do that one in my head yet. We'll maybe do it later. And then this is just simply minus 80. 20 times 4 is 80. Okay, that's just the positive one. Now we negate. So then we're negating this one, and this will be a minus 1 over 4. And then a minus will be, wait, yeah, minus a minus will be a plus 10 thirds. And then we have a minus 29 halves. It's pretty easy when it's a 1 there. All these becomes 1. And then you have a plus because it's minus a minus 20. Okay, that's that side. Now let's do this side. Hopefully that won't be too confusing. This will be a minus. Okay, now 5 to the first power is 5, second power is 25, third power is 125, fourth power I think is 625. So this will be a minus 625 over 4. And then a minus will be a plus 125 times 10 would be 1250 over 3 minus, because the minus out here, 29 times 25, I'm not going to do that one in my head right now, over 2 plus 100. Then we're going minus, so this minus will go away and you get the pluses here. 4 to the fourth, like we said before, would be, what do we say, 120, let's see, yeah. So I think this comes out 64 again. So plus 64. It's 128 over 4, which I think, no, 256 over 4, which I think comes out 64. I hope I'm right on that. Y'all have to check me on that. And this will be a minus. And basically, this is the same numbers you got here again, because here it was a plus here. Here it's a minus. So it's the same as here. So 640 over 3 plus 29 times 8 minus 80. Okay, so now I'm going to get the handy dandy calculator and see what we got. Okay, so let's go for it. Get my calculator set up, my phone shut off, get the calculator back. So that's going to be 64 minus 640 over 3 plus 29 times 8 minus 80. Okay, all that didn't get very far, but 2.2 2/3 basically. Minus 0.25, I can do that in my head, plus 10 over 3 minus 14 and a half, 14.5 plus 20 minus 625 over 4 plus 1250 over 3 minus 29 times 25 divided by 2 plus 100. I should have doubled those other things. I wasn't thinking. Plus 64 minus 640 over 3 plus 29 times 8 minus 80 equal 11.83 is what I got. Now they put it in fractional form. Okay, I'm going to jot this answer down. 11.83333, which is, by the way, 11 and 5/6. Okay, let's see what they got. They got 71 over 6. 6 will go into 7 one time. 6 will go into 11 one time, and 5/6. Yep, same answer. Okay, so yeah, 71/6 feet. Okay, the previous one was only 10 or 32/3 feet. Now, frankly, to me, those fractions don't make sense. First time was 10 and 2/3 feet. This time's 11 and 5/6 feet. Okay, yeah, the total distance was a little bit more, and that makes sense. Any questions on that? Was I too fast on the calculations here? Did you see how we got them? Yay or nay? I'm not usually too fast on anything. Okay, Jordan gave me a thumbs up, so I assume the others are okay with it too. All right, yeah, Brandon did too. Andy's still asleep. No, I'm just kidding. Okay, all right. So let's clear the screen. Any questions before we leave it? All right, I'm going to plug in my phone because I am using up the battery. Not much, but just I like to have it charged in case I have to do advising this afternoon. I want it fully charged. Okay, so let's see how they proceed. You'll have to ignore my writing because they write over it. I can't erase on this mode. Okay, there was what we got. Something very similar to what we had. Yep, it's exactly what we got. And then they did. They just magically got to 45/4 minus a minus 7/12 and came out with 71 over 6, which we determined was 11 and 5/6 feet, which is exactly what we had. Okay, and that was the last slide in this slide set, in this section. So, homework exercises here. And by the way, I haven't been mentioning these because I don't really do them in class, but it's not a bad idea for you to do. They're called the concept checks. They're at the beginning of every exercise set. I'll show you what I'm talking about. Exercise set 5.4, right there, 5.4 exercise. The first 4 questions are concept checks. Not a bad idea to look at those. Think through those. Make sure you understand what they're talking about. And I cannot keep this clip to my collar. I mean my pocket. I don't know why. The pocket must be just a little too small. Okay. Homework exercises here would be either 5 or 7. They're both at Calc Chat. Okay. Any of the odds 9 through 33. They're all at Calc Chat. 17's at Calc View. Either 35 or 37. They're both at Calc Chat. 35's at Calc View. Any of the odds 39 to 43. They're all at Calc Chat. 41's at Calc View. Any of the odds 45 to 49. They're all at Calc Chat. 45's at Calc View. 51 to 55, they're all at Calc Chat. 51's at Calc View. And then any of the odds, well, do 57 or 59, either 57 or 59, okay? Then do 61. And by the way, 57, 59, both at Calc Chat, should be. 61 is at Calc Chat and Calc View. 63 is at Calc Chat. 65 is at Calc Chat. Then do any of the odds, 67 to 73, they're all at Calc Chat. 69 is at Calc View. 75 to 79, all at Calc Chat. 75 is at Calc View. 81 to 85, all at Calc Chat. 87 through 91, all at Calc Chat, they should be. Then 93 through 97, they should all be at Calc Chat. 93 is at Calc View. And you can explore the doing either 99 or 101. That's up to you. There's plenty of them in this section, aren't there? 103 should be at Calc Chat. The error analysis, I don't really like them printing wrong answers in the book, but they put big red X's by them. See if you can figure out why they're wrong, what's wrong with it, what they did wrong. That's 105 to 107. If you enjoy doing that, do it. They should be at Calc Chat. There's a true false 109 that should be at Calc Chat. And then either 111 or 113 should be at Calc Chat. If you're up to the Putnam Challenge, knock yourself out. It's certainly there for you to play with, but I don't assign them. All right, that finishes finally 5.4. Let's move on to 5.5. Okay, I'm going to discard my annotations and close out this slide. And my screen sharing is stopped, so let me pick up I've got to get this out of the way because I can't read. Okay. I do not see, I just had it open. We could see it, so let me go back and pull up. I don't know why. That one. Okay. Now I have to minimize this and I don't know what's going on here. Why is this not opening up? Okay, let me try it again. Open the PowerPoint. Now, why is this opening? I don't know. Okay, go back to Zoom. Why won't it show up? Let me see what this one is. I don't know what that is. I still can't see it. Okay, tell you what I'm going to do. I'll get rid of this. Now this happened yesterday. This green block showed up in the middle up here, and I could not get rid of it. Okay, now let's see if I think I'm going to close out this. Here we go. Now let's see if I can get it. New share. There it is finally. Okay. Whew. That took a while to get them to do. We'll go from current slide. Now, can y'all see this one? Hopefully you can. Now I've got to move my taskbar out of the way again. This is such a pain in the neck. I move it and then it pops back up there. Okay. All right. Y'all can see my PowerPoints, right? Yay or nay? Good. Brandon said yes, so hopefully you all can. We're still in Chapter 5, Integration. If I can get the screen to advance. We're going to do 5.5 is integration by substitution. These are usually pretty fun. They sort of mess up at the beginning. Here's our objectives, plenty of them here. And this pattern recognition, maybe it's worthwhile. These guys are supposed to know what they're talking about, but frankly to me, just jump on in and do substitution. Why do pattern recognition first to find the indefinite integral? But we'll do it. We'll use the change of variable to find the indefinite integral. That's our substitution. Okay, we'll use the general power rule for integration to find the indefinite integral using substitution again. So I don't know why they break them out this way. And then they'll say use a change of variables. And is that box in the middle blocking out what you can see? It is on my screen. I don't know if it is on yours. Use a change of variables to evaluate a definite integral. That is another little step forward. You know, it's a lot like indefinite integrals, but there's a real neat way that you can do it. Sorry. All right, I turned on my ceiling fan earlier because it was getting a little stuffy here, but I'm going to turn it off for a moment. I probably will turn it back on later. And then finally, we'll evaluate a definite integral using the characteristics of an even or odd functions. Okay? Let's see. Yeah. So let's start with pattern recognition. Frankly, I find this portion of this section not really worth it, but I'll let you be the judge of this. In this section, you'll study techniques for integrating composite functions. Now, I don't know if you remember back in pre-calculus algebra when we did composite functions. And you probably thought at the time, oh, this is just another thing they have us do. What's the point in this? It's just something else. No. Here's where we're using it, okay? The discussion is split into two parts. Pattern recognition, which I see almost no point in, and change of variables, which is how you go. Both techniques involve use substitution, so why don't you just call it use substitution and go from there? Why do you split them up? Because they're both use substitution. I don't know. With pattern recognition, you perform the substitution mentally. Why? Okay, use the use substitution. It keeps you from making mistakes. And with the change of variables, you write the substitution steps. Why it advanced, I don't know. The role of substitution and integration is comparable to the role of chain rule in differentiation. In other words, we're unchaining, like you do an antiderivative, you undo the chain rule. That's what we're doing, okay? Now, going back to when we're talking about differentiable functions, if we had y is some function of u. Now, there's no reason they use the capital F here, I don't think, but it's okay. But u itself is a function of x, g of x. By the chain rule, if you were taking the derivative with respect to x of this here, we would first take the derivative of f at g of x, because that's what u is, and then take the derivative of the inner part, derivative of g of x. So that's what we did with chain rule. That's a review for Cal 1, okay? From the definition of an antiderivative, then it follows that if you happen to have the integral of something that's obviously, and this is why they use capital F, obviously, I still don't see the y, okay, but the derivative of a function evaluated at another function, followed by the derivative of that innermost function, you can just undo that in one fell swoop and say it's f of g of x. Of course, plus c. Okay? If you can see all that and it makes perfect sense to you, fine. But frankly, to me, there's so many parentheses, so much this of that, of that, of this, of that, it's so much easier to just do a U substitution and go with it. But we haven't talked about what that is yet. Let's go for it. These results are summarized in the following theorem. The antidifferentiation of a composite function. If g is a function whose range is an interval I, and f, this time it's a little f, be a function that is continuous on I, okay, on that same interval I. F is a function that's continuous there. If g is differentiable on that interval I, function whose, I'm sorry. This is the range of g, and that's the domain of f. Okay, I'm sorry, I wasn't paying attention. G is a function whose range is the interval I, so I should have put the range this way, interval I. Let f be a function that is continuous on that interval I. If g is differentiable on its domain, and capital F is the antiderivative of that little f, now it's back to like we were before, on that interval I, which is the range of g, then the integral of f of g of x, g prime of x, is simply capital F evaluated at g of x plus c. Now, if you see that without anything else and go for it, fantastic. Do it. Okay. Here's how we do it in reality. Let u equal the g of x, that innermost part. Then take a du. Du would then be g prime of x dx. Anytime you have a d on this side, you better have a d on that side. So this would be the derivative of u would be g prime of x times dx. This is written in differential form. You could have said du dx is equal to g prime of x. That's obvious, but we don't want it in that form. We want it in differential form. So it's du is equal to g prime of x dx. Now what you have is the integral of f of u du. And that integral is obviously the antiderivative of f, which is this capital F evaluated at u. But u was g of x. And then, of course, it's an indefinite integral. You do a plus c. Again, a lot of blah, blah, blah. Actually, working some like that it's so much easier to just do the u substitution and go with it. They are actually fun. Okay, so let's do them. Example 1 shows how to apply that theorem directly by recognizing those things. Okay. Note that the composite function in the integrand has an outside function f and an inside function g, just like we talked about it in the chain rule. Moreover, the derivative g prime is present as a factor in the integrand. So the outside function is f, the inside function is g, and the derivative of g is here. Okay? And if that's the case, then you can, they say, go immediately to the antiderivative of f, evaluated at that innermost function, g, and remember to put your plus c. Now, do I do it that way? No, I do a u substitution and go from there, okay? I see no reason to fiddle around with this so much, okay? So here's what we do, okay? Let me get my pen in hand and do it. Here's example 1. All right. Now, if you have a tendency, I can't find my pen, there it is, to square this, like it says, and then multiply it by that, you come up with a polynomial, you can take the integral of that polynomial. Frankly, though, that's a lot of work. It's doable, and it's completely correct. But if you notice that here you have an innermost function here, and there you have the derivative of that innermost function, then I say this: let u equal, now here's how I say it, the innermost part of the most complicated part of your integrand. Most complicated part, of course, is this squaring function. The innermost part of that is here, so let that be your u. Let u equal x squared plus 1. As soon as you determine that, any let is followed by then. Then du, anyone tell me what du is? Derivative of x squared. 2x in differential form, dx. Now the magic happens. Here is your u right there, and here is your du right there. So you can rewrite this integral as the integral of u squared, because you see this thing here is squared, du. Well, I think I can do that one. What's the antiderivative of u squared? Perfect. Okay. Plus c. Don't forget, it's an indefinite integral. All we do now is plug back in what u is. So this is x squared plus 1 cubed over 3 plus c. There's your answer. Without having to square the binomial, multiply it by 2x, then take that polynomial and integrate it, and you'll get something really big, long, and hairy. And then you have to recognize that comes out into this simple form here. This is the way to go. Use substitution. They like to say, oh, look at this and see if you can visualize it or recognize the pattern. Yeah, if you can, go for it. Okay? Use substitution. It does all the work for you, and it's just what, 2 steps, 3 steps? You got it not. Let's see how they do it. They write all this down, let g of x equal that, which is fine. We called it u. Okay, it's so much easier u. To obtain g prime is 2x. Yeah, we said du was 2x dx. Okay? Okay. Then f of g of x would then be what your first part of the integral is, and then the second part of it. From this, you can recognize the integrand followed this pattern. Oh my goodness, we'd already be through with the problem before we did this, okay? And then you can say, using the power rule for integration, theorem 5.13, you can then write this down, and they got 1/3 of this plus c, which is the same thing we got, except I wrote it over 3. X squared plus 1 cubed over 3, they wrote 1/3 x squared plus 1 cubed plus c. Now, here's where I usually jump up on my little soapbox and say, if you had written the answer like this, you had been working this in WebAssign, written the answer like this, they'd have said wrong answer. If they were looking for this answer, they're exactly the same answer. Okay, so that's why I don't like the packages like WebAssign. They'll tell you something's wrong when it's absolutely correct. Okay, this is no better than the way we had it. In fact, I think the way we had it's a little simpler. Any questions on that? Use substitutions come in so easy, so handy sometimes. Okay? It says try using the chain rule to check the derivative of this, and that would be easy. 3 times 1/3 is 1 times x squared plus 1 to the second power. Then the chain rule says take the derivative of the inside times 2x. That's exactly what you got. X squared plus 1 to the second power times 2x dx. So sure, and the derivative of c is 0. Okay, so you get exactly what the integrand is. Okay. Now, I'm trying to see where they're skipping example 2. So let's go back a slide and let's go to the whiteboard. Still haven't seen Ashton today. Have y'all seen him try to get in or anything? Heard from him or anything? All right. Here's my whiteboard, so I've got to do some more manipulating here. I'm going to take this toolbar that you can't see and move it out of my way. I'm going to check and make sure Jordan isn't sort of in the way. No, he's fine. Okay. And then take my whiteboard and scoot it as far to the left as I can, because your names and blocks with your names in them are in the way and my picture's in the way. So that's about as far as I can. You probably just see a white screen and say, what's he doing here? Well, I have something I have to manipulate. So let's do example 2. Here's example 2. Find this integral. The integral 5 e to the 5x dx. Okay. Now, get this heavy book off my lap. All right. Now, we do have a composite function here. It's the exponential function, but its argument here is a product function. Okay? So, like I say, if you're trying to go for a u substitution, which looks like a good idea here, let u be the innermost part of the most complicated part of the problem. Well, the most complicated part is the e. The innermost part of that is 5x. So let's let, this pen is really jumpy today, let u equal 5x. Anytime you have a let, follow it with a then. And the then is always the derivative of that u. And what's the derivative of 5x? Anybody? 5 something else. You have a d on this side. You have to have a d on this side. 5 dx. Derivative of 5, 5 is just a constant, pull it out. Derivative of x is dx. Okay? Now, look up here. Here we have e to the u, and the 5 dx is your du. So this is just simply the integral of e to the u du. You see, this is e to the u. The 5 dx becomes your du. And I think even I could probably figure out what the antiderivative of that is. Anyone might want to make a guess? Antiderivative of e to the u. It's my favorite of all time. Exponential functions, the derivative is themselves, the antiderivatives is themselves. It's just e to the u. Of course, plus c because it's an indefinite integral. But now we just plug back in what u is, or u are, and that's 5x. So this is the same as e, yuck. There's things that pop up on my screen that are just aggravating. E to the 5x plus c. If you want to check it, just take a derivative of that. That's e to the 5x times 5, and that's exactly what you got here. 5 times e to the 5x. Got it. Any questions on that? These are sort of fun, aren't they? Okay? Seeing if they pan out. Of course, they'll find ways to make them more complicated, but so far, we've got it. So, our answer is e to the 5x plus c. Got it. Now, I wish that they did include the box at the bottom of page 333 in the slide set. They did not. Okay? And it's a shame they didn't. Okay? Because this is sort of fun to do. Let me write them down for you, because it is sort of a good exercise. They didn't do them, but let's do them. Here's the first one. We're not going to solve them, we're just going to write them down. The integral of 2x times x squared plus 1 to the 4th power dx. Okay? Do you see what would be your choice of a u substitution? Okay? Let u equal what? Okay? In my mind, find the most complicated part of that integrand. That's this thing raised to the 4th power, right? Let the innermost part of that be your u. So there is the u right there. Let u, let equal. Let u equal x squared plus 1. Anytime you have a let, follow it by then. Du is equal to, anyone want to make a guess? 2x dx. You got it. Very good. And now you see the 2x dx up here. There's your du, and this is u to the 4th power. So this now becomes the integral of u to the 4th du. And we know what that is. It's u to the 5th over 5 plus c, and then instead of u, you put x squared plus 1 to the 5th over 5 plus c. It's done. Okay? How about this one? The integral of 3x squared times the square root of x cubed minus plus 1 dx. Okay? What do you reckon your u will be? You choose.
X cubed plus 1.
Excellent. Okay, x cubed plus 1. The innermost part of the most complicated part of the integrand, and that's the square root. Innermost part of that is that. So then, always follow the let by then. Du is equal to anybody? 3x squared dx. Perfect. Isn't this fun? Here's your 3x squared dx. That's the du. And this is, I'm going to rewrite the integral to be this. U, that's the inside, to the 1/2 du. Whoops, that's a u. Okay. And anyone know what that integral would be? Increase the exponent by 1. It's just a power rule. By 1. 1/2 plus 1 would be 3/2, and divide by that new exponent, which is the same as multiplying by 2/3, and then plus c. Okay, but then go on and plug in what u is, or u are, okay, and that would be 2 times x cubed plus 1 to the 3/2 power over 3, or 2/3 times x cubed plus 1 to the 3/2 power plus c. There's your answer. How about if you had a trig function here? Will that work too? We sure hope so. If I can get my pen to show it. There it is. Okay. The integral of secant squared x tangent x plus 3 dx. Now this one, this one might throw you a little bit, because it's sort of a toss-up here. Which is the more complicated looking part of this? Is it the secant squared x, or is it the tangent x plus 3? What would you say? Believe it or not, it is a tangent x plus 3. And here's why. You'll see in just a minute. Let's do that. Let u equal tangent x plus 3. Always follow the let by then. du is equal to what? Now we get into how well we remember our trig derivatives. Anyone remember what the derivative of tangent is? Oh, please say yes. Otherwise, I'm going to have to talk to your Cal 1 teacher. No, I'm just kidding. Derivative of tangent is indeed secant squared x. Go back and check. It's probably at the front inside cover of your book, I think. That page, that sort of cardstock page that's perforated at the very front of your book, basic differentiation rules, number 15, front inside cover, derivative of tangent u is secant squared u du. So there we have it. Secant squared x. I didn't do the last part, what I always fuss to you about, dx. If you have a d on one side, you have to have a d on the other side. Okay? So then this becomes u du. Okay? That integral would then simply be the integral of u du, which is u squared over 2 plus c, which is tangent x plus 3 squared over 2 plus c. I said I wasn't going to do this. Now that 2 plus c is not in your denominator. I just ran out of room because Brandon's in the way again. So, but anyway, that's how it works. Okay. Now, here, I'm going to erase this. Anyone need that left up here any longer? So I'm going to erase that. Here are some that are similar. I told you they'd find some way to make it a little more complicated, and it wasn't very hard for them to find either. Here's the integral of x squared plus 1 to the 4th power dx. Now, only a minor little difference here, but you start the same way. What would you say the u should be?
X squared plus 1.
Excellent. X squared plus 1. Then, always follow the let by then. Du, and I think someone may be trying to come in. Are they? My thing just popped up down here. Let's see. No, we just lost somebody. Goodness, who was it that was here? Oh, Mr. LeBlanc. Brandon must have had to get out for some reason. Okay. Hopefully he'll be back. Hold me just a second. I need some water. My throat's dry. Okay. Now, so what's your du? If that's your u, which you chose, what's the du? What's your du? 2x dx. Now here we see a little bit of a concern here. We don't have a 2x dx up here, but we do have an x dx. So let's divide both sides of this by 2, and that way we have what x dx is. It's 1/2 du. So what we'll do here, have the integral of x squared plus 1 is u So that's going to be u to the fourth. And your dx, or x dx, is 1/2 du. Well, that 1/2, I don't have to put an integral. I'm going to put it out here and just put the du here. So here we have 1/2 of antiderivative of u to the fourth is, anybody? Whoa, 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 here's somebody trying to come back in. I can't see. Brandon is trying to come back in. Let's see if I can let him in. Yes, he's back. Welcome back, Brandon. I already had you present today, right? Yes, it's only Ashton that we're missing. Okay, has anyone come up with what the antiderivative of u to the fourth? I know it's blocked out right now. What would that be? U to the fifth over 5. Yuck, this thing is so aggravating. Okay. Plus c. Alright, so this will be 1/10 x squared plus 1, that's your u, raised to the 5th power, plus c. And there's your answer. Now, I said I wasn't going to work them out, but I thought we would do that one. Okay? Now, we won't work out the rest of them, maybe. They're so much fun, it's sort of a shame not to. Here's the E problem. The integral of x squared times the square root of x cubed plus 1. See, these are very close to what others we looked at, just a little different. Dx. What would you choose to be your u?
X cubed plus 1.
Excellent. It's just like before, x cubed plus 1. Then, always follow the let with a then. Du is equal to help me.
3x squared plus c. Not plus c, but
dx. Dx. Perfect. Okay. Now, we have an x squared dx. We don't have a 3x squared dx. We'll divide both sides by 3. So we do have an x squared dx. And then this becomes the, and bring that 1/3 on the outside. Just do that because you don't need it in the integral. And your integral will be the x squared dx will make up the 1/3 du. I already got the 1/3 outside, so that's just going to be a du here. And then this is going to be u to the 1/2 power. And we remember how to do that one, right? Please say yes. We basically did it exactly the same way before.
2u raised to the 3 over 2 over 3.
Yeah, 3 over 2. Yeah. But multiplied it by 2 times 2 over 3. Yeah. It's 2/3 u to the 3/2 power. And then plug in what u is, x cubed plus 1. Okay? Now this next one, yuck, where is it? There we go. The integral of 2x 2 secant squared x times tangent x plus 3 dx. And again, just like before, you let u be this, du will be secant squared. This 2 is not even necessary. Put it on the outside. And then just proceed like we did before. Derivative of tangent is secant squared, so you have x dx. So you have u du, it's u squared over 2, just like before, only since you had a u squared over 2 before, let's carry this one on out, it's sort of fun. come on, pen, where are you? There you are. Just like before, let u equal this part over here, tangent x plus 3, then du is equal to secant squared x dx. Okay, and there's your secant squared x dx. So this integral becomes the integral, twice the integral of u du, which would be twice, this would be u squared over 2 plus c, and the 2's cancel out here, so you just are left with tangent x plus 3 squared plus c. Whereas the last one had a 1/2 in front, we don't need it there anymore. Alright, they didn't do those on the slide set, but I thought those were pretty fun to do, and they're going to jump right in and have you do that in a minute. Okay? Now, set this down for a moment, get this heavy book out of my lap, and let's go back to our PowerPoint. There we are. And we'll go back to current slide. Okay, now, top of your page 33, this paragraph, they didn't do example 2 on the slide set, so they just said the integrand in example 1, but it was also 1 and 2, fits the integrands in that fit the model, the pattern exactly. You only had to recognize the pattern. So what? You can extend that technique considerably with the constant multiple rule, and this is really what we did on that last one. When we had a 2 secant squared x times tangent x plus 3, we just pulled the 2 on the outside and then proceeded to do that. Many integrands contain the essential part, the variable part of g of x, but are missing the constant multiple, just like we saw before. Sometimes we divide by 2 or divide by 3 or something like that. In such cases, you can multiply and divide by the necessary constant multiple, and that's what example 3 is going to show, which is basically what we were just doing. So here's example 3. Find the indefinite integral. Was this the same one we did? No, not quite, but awfully close. What would be your guess to do? You tell me how to start. I'll write down the first word. Let. Pick it up and carry from there. Excellent. X squared plus 1. The innermost part of the most complicated part of the problem. Follow that with a then du 2x dx. Done. Perfect. Now, notice up here we have an x dx, but we don't have a 2x dx. So let's divide out the 2. Now, they like to say multiply and divide by that. That's fine, but why make it that complicated? Just divide by 2, and now what you have here is your x dx, which is your du over 2. So this would then become 1/2. Pull that 1/2 on the outside. The integral of the u is x squared plus 1 squared. So this is u squared, and the x dx was the du over 2. We already pulled the 1/2 outside, so it's just du. And I think I could probably even do that one. What would that be? I'll write down the 1/2. Antiderivative of u squared du. Anybody? Come on. E. Perfect. U cubed over 3 plus c. So here, let's pull the 2's and the 3's out. That would be 1, 6. U cubed, u is x squared plus 1. So that would be x squared plus 1 cubed plus c. All right. I think that's what the answer is. Let's see what they think it is. Similar to the integral in example 1, except the integrand is missing a factor of 2. Now, recognize that 2x is the derivative of that. You can let there, and what they do here, which is fine, is the only reason they multiply and divide here is to get their pattern recognition done and get the 1/2 on the outside, leave the 2x on the inside because that's where you want it. But my goodness, isn't that just going to around your elbow to get to your ear? I mean, it's perfectly correct and doable, okay? And that would be this is the same thing we got then. The integral is 1/2 the integral of f of u du. That's what it comes down to. They just like to not put the u's and the du's in there. I don't know why. It's so much easier. To me, it's so easy to get this confused. But if you like it that way, go for it. Same thing we got. Last step, 1, 6, x squared plus 3, x squared plus 1, raised to the 3rd power plus c. Exactly the same answer that we got here. 1, 6, x squared plus 1, cubed plus 3. There it is. 1, 6, x squared plus 1, cubed plus 3. Plus c. I said 3. Plus c. Any questions on that? Going too fast, or is that okay? All right, so there's example 3. All right. They do have a little blurb at the bottom of the page. In practice, so most people would not write as many steps as shown here. I certainly wouldn't, okay? You've seen how I do it, so go for it. Now, they do make the emphasis here, and I almost wish they hadn't even brought this up, because here they say, don't do this. Well, that's like me saying, don't think of a big black horse. I bet you every one of you thought of a big black horse, didn't you? Okay, that's why I don't like them bringing up things like this. But they say that constant you can pull out is only constants. You can't pull out a 2x. You have to pull a 1 over 2x. You have to pull out a 1 over 2 only. Only thing you can pull out of that is numerical values, not variables. Just remember that. All right. So that was example 3. Now we're moving to change of variables for indefinite integrals. That's what we've been doing, okay? It's a u substitution. Call it a change of variables. That's what we've done. With a formal change of variables, you completely rewrite the integrand in terms of u and du. Frankly, that's the way to go in my book. That pattern recognition, at least so many places you can make a silly little mistake, and it's kind of complicated, and you will lose that mistake in there. So I like to do the u's and du's. It's so easy. Although this procedure can involve more written steps than pattern recognition, I don't think so. It is useful for complicated integrands. The change of variable technique uses the Leibniz notation for the differential, not derivative, differential. That is, u equal g of x, and du is equal to g prime of x dx. I don't even think in terms of g's. Just u is equal to whatever that expression is, du is whatever its derivative is, okay? They just make it seem so complicated. And that's what it turns out being, just like we were doing. So let's do example 4. I'll ask you what you think the first step should be. Anybody? U equal 2x minus 1. I like it, because it's the innermost part of the most complicated part of the problem. The square root's the most complicated part. That's the innermost part. Follow the let with a then, and that gives you 2dx. Perfect. Okay, now all we have is a dx up here. We don't have the 2, so let's divide out the 2's down here. Okay, now we have our dx. It'll be a du over 2. So what this becomes now is take this 1/2 on the outside, just the numerical part, 1/2 the integral, and rather than write this as a square root, I want to write it in exponential notation, so that would be u to the 1/2. Now that's not skipping too many steps, is it? And then what we had left was a du over 2, but we already pulled the 2 out here, so it's du. And that's something that I think even I could do. What would that be? Antiderivative of u to the 1/2? Anybody? Anyone? 3. Get out of there. U to the 3/2. Increase this by 1, and then divide by that new exponent, which is multiplying by the reciprocal, 2/3. Okay? And then don't forget your plus c. Now, notice this 2 and that 2 can divide away, and this gives you 1/3, and u is, or u are, okay, 2x minus 1 to the 3/2 power plus c. That's it. Okay? And if you had been doing that before, it just goes so easily into this. You don't have to wait. No, let's see, I can't do a pattern recognition, so let's do this. Just do a u substitution. That's what pattern recognition is. Do the u substitution, get used to do it on the easy ones. Comes out pretty handy for the harder ones too. Let's see how they did it. So first, let the innermost function, 2x plus 1, be your u. Exactly like y'all said. Let u equal 2x plus 1 minus 1. Okay, then calculate the differential, du, and that would just be 2dx, just like you said here. Now, using that the square root of 2x minus 1 is the square root of u, and I wouldn't even do that. I would write it as u to the 1/2 power. I would have done that. They just kept it here. Dx is du over 2, so this was that, and this is that. Again, they're putting too many steps in here. So easy, just pull that to the outside and write that as u to the 1/2. I don't know why they insist on doing this, but maybe it's easier to see. I don't know. Okay, so pull out the 1/2, then write this as u to the 1/2 du, and that's just a power rule. Be 1/2 u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, and they magically write it as 1/3 u to the 3/2 plus c. That's the answer. And that's exactly what we got. 1/3 2x minus 1 to the 3/2 power plus c. I'm sorry I didn't take it one more step. There it is. 1/3 2x minus 1 to the 3/2 power plus c. Usually if they give you the problem in x's, give the answer in x's. Don't leave it in u's. Go on and plug in what u is, or u are. All right, any questions on that? That was example 4. Let's see what happens. They're skipping, wow, they're skipping 5 and 6. So let's go back and do examples 5 and 6. Oh, we'll do 5 first. Let me take us to the whiteboard. All right, we go to 11:40, so don't let me forget. We got about 16 minutes. All right, to clear my scratch from before. Okay? All right. Here's example 5. The integral, or the antiderivative of x times the square root of 2x minus 1 dx. Now this is amazing to me. Okay, now first, before I say anything else, I will give them a little credit here and say this example 5, they happen to write here example 5. Is that it? No, that's example 4. Here's example 5. I can't read it. See larsoncalculus.com for an interactive version of this type of example. I will give them credit for that. But what I find really irritating, they just did example 4 on the PowerPoint, and that was a pretty easy example. Now they're introducing one that has a subtle but very definite change to it. Okay? You've got some manipulation to do here we haven't done before. Now, where would you get started? That is a great start. 2x minus 1. Okay? And then follow that by then. Du equals 2dx. And here we see our problem. Here we have a d. Okay, we can divide away the 2. That's no issue. We've done that before. Okay. But what do we do with this x here? Well, here's the trick. And this, they should have, I think, explained something to you before they just give it to you as an example. So here's what you do. You see this up here? Let's take this formula and solve for x. This equation and solve for x. So what we're going to do is add 1 to both sides. Okay, and that will give us u plus 1 is equal to, because these add to 0, 2x. Well, I just want an x there. Okay, so I'm going to divide both sides by 2, and that gives me x is equal to u plus 1 over 2. Okay, now let's go back to our integral then. Now remember, we got a 1/2 from here, but we also have a over 2 from here, so that's a 1/2 and a 1/2, so this is a 1/4 on the outside, times the integral of, your x is u plus 1 over 2, but we already took care of the 2. So that would be a u plus 1. Get out of there. Okay. U plus 1. And then your radical, I'm going to write to the 1/2. That's just u to the 1/2 power. And then we've got our du. It was a du over 2, but we pulled the other 2 out here. Now, there is an integral that we can do. Now, you might not recognize it, but it is. Don't forget that 1/4 out front. Okay? Now, what we're going to do first, before we do, is distribute that u to the 1/2 here. So u to the 2/2 times u to the 1/2 is u to the 3/2 plus 1 times u to the 1/2 is u to the 1/2. That's your du. Alright, in that form, I think probably I could do it, but let's see if you can. antiderivative of u to the 3/2. Power rule, increase that by 1. 1 is the same as 2/2, so 3/2 plus 2/2 would be 5/2. But then divide by 5/2, which is the same as multiplying by 2/5. Okay? Sorry. Plus, same thing here. This will be u to the, what's your exponent here? Increase the 1/2 by 1, or 2/2, and that would be 3/2. So multiply that by 2/3, because that's supposed to be a 3 there. Okay? Plus c. Now, we happen to notice this has a 2 in it, that has a 2 in it. We can factor out one of those 2's. We still got 1/2 left. Now we have 1/2, or actually I think they're going to write it like this. 1/10, 1/2 of 1/5 is 1/10, and then what is your u? 2x minus 1 to the 5/2 plus 1/2 of 1/3 is 1/6 times 2x minus 1 to the 3/2 plus c. That's how I would write the answer. Let's see how they did. I bet you it's some other convoluted way, but let's see what they've got. Example 5. Oh, amazing, amazing. We wrote it the same way. 1/10, 2x minus 1 to the 5/2 power plus 1/6, 2x minus 1 to the 3/2 power plus c. Perfect. Any questions on that? You can't take this x outside because that's what you're integrating. You can take fractions out, this half and that half, take any whole number out or any numerical value out, but you can't take that out. So, but since you're u substitution here, you can manipulate that, solve for x, and then plug that value in for the x. Get rid of that 1/2, take it on the outside like we had. That became part of that 1/4. And then this was simply u plus 1 times, and this part was u to the 1/2. Now that you can distribute. This you can't distribute. You can't distribute x times 2x minus 1 to the 1/2. No, that won't distribute. This will distribute. Okay? Just multiply the 1/2, u to the 1/2 times each term inside, and proceed from there. Does that make sense? All right. Any questions before I clear it? All right. We're going to try to get example 6 done before we run out of time. Okay? So if it's okay with you, I'm going to clear the drawings. Is that fine? Okay. Here's example 6. Find this integral. The integral of sine squared x, or sine squared 3x times cosine of 3x dx. Okay. How would you begin this one? All right, that was a good guess. However, all right, again, this is one they didn't have on the slide set, and yet it's another wrinkle in it. Now, If you can do this in your head, you can just do one u substitution. But if you need to, do two, except maybe make the second one a v substitution or something like that. Use a different letter. I'm going to try it just with the 1. Now here's the deal, and this is where the idea of pattern recognition comes into play. Which is more complicated, sine squared or cosine? I would say the squaring function is more complicated. So let's do the innermost part of that squaring function, which would be the sine of 3x. Now, someone might argue, no, the innermost part would be 3x. And if you did through 3x, that works too. But let's see if we can do it this way. Then du is equal to, what's the derivative of sine of 3x? Anybody? Derivative of sine is cosine, but because this is a composite function, then the inner part, chain rule, would be a 3 on the outside. And then there's your dx. And sure enough, that's where the cosine 3x comes into play. Now, we don't need a 3 there, so let's divide that out over here. Okay, so what do we have now? That 1/3 can come on the outside, and then you have the integral of, this is u squared, and this part here, when you got rid of these 3's, was du. Du over 3, but we already took care of that. Du. That's a fairly simple one to do, I hope. And what would that be in terms of u's?
U cubed over 3.
Perfect. Plus c, and this would be 1/9. I would combine those 3's together, and then what's a u? Sine of 3x. So that would be sine cubed of 3x plus c. That's what I'm guessing the answer is. Let's see what they got. Yep, 1/9 sine cubed 3x plus c. Okay, and you can go back and take derivatives and you see that's what's happening. All right. Oh, look at that. We've still got several minutes left. So any questions on this one? Do I need to leave it up there a little longer, or do all of you have it? Okay, I don't hear any objections, so I'm going to clear and go to a new share, go back to our PowerPoints, and go from current slide here, and we got 2 minutes left. Let's move along here. Here are the guidelines at the bottom of page 336. Okay? Steps used for integration by substitution are summarized in the following guidelines. First, choose a substitution, let u equal g of x. Okay? Yeah, if you think in terms of g of x, that's fine. What I say, find the innermost part of the most complicated part of your integrand, let that be your u. Okay? They call it g of x, that's fine. Usually it is best to choose the inner part of the composite function, such as the quantity raised to a power. That's what I was saying. So once you get the u, then do du. Let u equal this, then du is equal to whatever the derivative of that innermost part is, with a dx after it. Now, hopefully then, you can rewrite the integral in terms of the variable u. Hopefully, something here will look like what's inside the integrand. If you need to manipulate some numbers there, do that. Find the resulting integral in terms of u. Now that x that we had in that one, yeah, go on and figure out what that is in terms of u. Replace the u by gx. Okay, I guess what they say, solve the integral, okay, in terms of u, and then go back and put the, instead of u, put whatever function that was in for your answer that you had in u, and then check your answer by differentiation. So that's exactly the steps we were following. I don't like the way they worded some of them, but that is what we were doing. Okay? Now, I think we just ran out of time. So we'll start next time, top of page 337, general power rule for integration. Okay? Whoa, I almost lost my ionizing pen, dropped it, and those are very expensive, so I don't want to do that. Let me erase this and mark my page here and see how far we got. We got good progress done today. So in exercises 5.5, starting on page 341, do either 5 or 7. They're both at Calc Chat, 5's at Calc View. Do any of the odds, 9 through 27. They're all at Calc Chat, 15's at Calc View. Do either 29 or 31. Now we didn't actually do a differential equation, but I don't think they're going to have that in the book either. I don't know why they threw things in like that, but try to do that. If you can't, ask it in class and we'll do it. 33, we didn't do one like that, but if you want to, we can try to do those in class. See if you can do them on your own. But then I think you can do any of the odds 35 to 41. I mean 35 to 55. Sorry about that. They're all at Calc Chat. 41's at Calc View. And again, this is not one they're doing in the book, but if you want to try it, try any of the odds 57 to 63. I sure don't see any of these examples like this in the book. So try to do those too. If they give you problems, bring them up. So 57 to 63, they're all at Calc Chat, 59's at Calc View. We'll stop there and pick up change of variables next time. All right, any questions? All right. Sorry we went over 2 minutes, but there'll be no extra charge today. Those are going to be free for you. If you have no questions, I'm going to stop sharing. I'm sick and tired of sharing here. And if there are no questions, I'm going to end the meeting. So what you think? Any questions? All right, we'll see you then. Oh, man, first time we met this week, and I say, have a good weekend. Okay, we missed you on Monday. Have a good weekend. Take care. See you Monday. Bye-bye. Hey, Laron. Good to see you. Any questions, issues, problems, concerns before we start recording or anything today? Oh man,